the meeting. Wow, I love that. I'm going to say something I'm not proud of. I did not want to come to school today. I'm not proud of that. Usually I like coming to school, but I just did not. I woke up this morning and said, I don't want to. I know that happens to you guys too. And I drove, and I hate driving to school. So, but I had no choice. I took so much stuff home. I was afraid that if I tried to drive it all with my bicycle, that I was going to lose something, like fall and break something. Because I probably wouldn't break. I'd probably, throw myself into a ditch so I wouldn't break my computer, but probably would just destroy half myself. So, all right. So we've got D here. We've got, let's say there's an electric potential difference between A and B. We'll just say that the electric potential difference is V. And we have the area of the plates, capital A, and charge on the plates of Q. So there are just a dozen different ways this idea is presented. So let's make sure we talk about a variety of things. And when you guys are taking notes on this, please consider the different ways they do this. Because the first is there is doing this problem where the potential difference is maintained across the plates, which means they don't isolate the capacitor, they leave it connected to the battery and ask this question. Then there's the possibility where the capacitor is isolated, removed from the potential difference, and ask the same question again. I think it's not a surprise that moving the plates is going to change the separation distance, which is going to change the capacitance. And if I change the capacitance, I'm changing either voltage or charge. And at this point in your notes, you should be able to, I'm hoping the discovery's already happened. So you could just say it like this, that if it's connected to a battery and you change the capacitance, you will change the charge. If it's disconnected from a battery and you change the capacitance, you will be changing the potential. You should get that in your head. So I'll say it one more time. If you leave it connected to the battery and you change the capacitance, you change the charge. If you disconnect it from the battery and you change the capacitance, you change the potential. So we're going to do this problem right now with the potential difference being maintained. Now, the next thing is to realize they don't have to ask it in terms of charge. They can just as easily talk about this question in terms of charge density. And you should be able to be flexible enough in these problems to recognize that it's not really much different. So if they give it to you in terms of charge density, fine. If they give it to you in terms of charge, fine. You should already know that the capacitance of a parallel plate capacitor obeys this relationship. And we've been pretty clear that the definition of capacitance plays a distinct role when we're dealing with changing the capacitance. So those things should be called up in your mind. But there's other things that you should start recognizing are going to play a role here too. And that is there's an electric field between the plates. And that electric field is not arbitrary. At this point, this electric field is well known to us. The electric field has to be equal to E times D. I don't have to do the integration here. It's a parallel plate capacitor, so the electric field is constant between the plates. So although this is derived from taking the integral of E from one plate to the next, if E is a constant, it's just E times D. So I really want you guys to understand we use parallel plate capacitors because this stuff is much easier to contemplate in when we deal with parallel plate capacitors. Everything's a nice constant value. So the first thing that we should recognize is that you have a charged plate in an electric field. So the definition of force is still based on Q times E. Everything here is a constant, meaning I'm not having to do any integrals. So I can begin to start kind of combining these in any way I want, depending on what information has been given in the problem. If I want to see the force, on the plate from the electric field, then I just need to put the electric field in terms of other things that I have. For example, I could put this in terms of Q times V over D. Now I've got the force on the plate in terms of the potential. If I want, I could change that. Maybe I'm not allowed to put the potential in there. Maybe I have to have it in terms of the capacitance. Okay, well, I've got a way of doing that too. I could reorganize this in terms of capacitance and then substitute it in, and I would get, now I have two different Q's here. I probably should draw them the same. So I'll get Q over D times Q over C. And then this is just going to be Q squared over DC. Now, maybe I'm not allowed to have it in terms of the capacitance. Maybe I have to have it in terms of like the area of the capacitor. Well, I was told it was a parallel plate capacitor, so I've got an expression. I can put that in for C now. So when I do, I'll get that the force on the plate is equal to Q squared over D times D over kappa epsilon naught times the area of the plate. The D's cancel here. And I get this kind of curious response where I get Q squared over kappa epsilon A. The first thing I want to point out here is if you look at this function, as long as the potential is maintained, the force to pull the plates apart doesn't change as the plates get pulled apart. And the reason is because we've made the assumption that the electric field from a infinite sheet is constant. So the force to pull the plates apart shouldn't change since the electric field is a constant. Why is Hillsborough County calling me in the middle of the school day? Don't inquiring minds want to know? Hello?
This is Mrs. Freitas from Sickles High School calling with an important message. We've been notified that a student at Sickles has tested positive for COVID-19. However, I want to share that this student has not been on our time.
I have to laugh. That's all I got left. So the reason I hope is clear. Once we know the electric field is constant, we should be able to get an expression for the force that is independent of the separation distance because the electric field isn't changing. Remember, we go right back to this. The electric field is a constant, therefore the force is a constant. So I have an expression now that tells me the force on the plates in terms of the charge on the plates and the area of the plates and other constants. Now, I don't know which one of these would be asked on the test. It really depends on what they wish to kind of call your attention to. But here's an important thing. It looks to me like if I start pulling the plates apart, although this means the force is constant, that doesn't mean that things don't change when I start to pull the plates apart. The capacitance is clearly going to change when I start to pull the plates apart. And the electric potential between the plates is going to change as I start to pull the plates apart. All of that has to be true. If the plates get further apart, the electric potential increases. That's right here. D gets bigger, so the electric potential has to increase as well. Capacitance, though, gets smaller. So there's a lot of things changing here when I start to pull those plates apart. But the fact that I could actually calculate the work to pull the plates apart is also pretty fascinating to me. Seems to me that the force is a constant, which means it will take energy to pull the plates apart. I will have to do positive work in pulling the plates apart. That's not lost on me, and it shouldn't be lost on you. I am taking two things that are charged, and I'm having to separate them, so it's going to take energy to do so. So the amount of work is pretty straightforward here. I'm going for separation distance 1 to separation distance 2. I kind of skipped the calculus, but I thought I could here. If I shouldn't skip the calculus, tell me, and I will do more steps. So I'm good. Now, this work should show up as a direct increase in the energy stored in the capacitor, meaning I should be able to apply the definition of potential energy and see the change in energy in the capacitor due to what has changed by my increasing the separation distance. But I want to stop right here and say first, this is everything related to pulling apart a capacitor. Questions about this? Yes, sir.
So for your second force equation, you know that D is good, like for the bulk apart, D would increase and C would decrease.
Yep.
They're like proportional to each other because in the third one you're able to like get rid of the fact that the force is changing both apart.
I'm sorry, Dylan. Can you say, I missed part of what you said.
Okay, so for the second equation, you know how like if you pull it apart, D would increase and C would decrease. But since in the third one you could like get rid of them and like so that the force wouldn't change.
Right?
You increase, that means that the D and C are proportional to each other.
Yes.
Okay.
Dylan was asking if D and C are proportional to each other. And that's why when you change one, D increases and C decreases. Is that why they go away? And that's why they go away. Yes. Because the proportion to which D changes is the same as the proportion to which C changes. Now, there is one huge glaring issue here. And I didn't make it clear. But in this example, specifically, would Q stay constant? Max? Right. One of these is applicable to when it's connected to a battery, and one of these is applicable to when it's not. So this, if we look at these, we want one in terms of V when it's connected to a battery and not Q. And we want one in terms of Q when it's not connected to a battery. Because when it's not connected to a battery, the charge stays the same. When it is connected to a battery, the voltage stays the same. So in looking at these, we've solved for one with the assumption that we're going to have the charge staying the same. And that's what makes it a constant. But if we wanted to deal with the voltage staying the same, we would probably have to put this in terms of something that has just voltage in it, which isn't hard. We just come back from the beginning, and instead of getting rid of V, we go back through and try and get rid of Q. So I think we should take a look at doing that. So this one assumes isolated because we have it in terms of Q. I think that's what the problem in the text was wanting. So now let's do one that's not isolated when it stays connected to the electric potential, so the potential stays the same. So are we okay? Am I going too fast? I'm trying to be very deliberate, and I don't know if I am. You okay there, Alex?
I was just going to ask on the work equation, what's D2 and D1?
Some starting separation distance to the next separation distance. I didn't know what else to say. And I was kind of, this part I think is the least interesting because they didn't ask it in the problem, and we tend to not see this question like this. But I just wanted to make up two, because there has to be a starting separation, and then we're pulling it to a new place. We could have just said 0 to X, but it seemed more reasonable to go from D1 to D2. Is that okay? So that Alex's question is where I got the D1 and D2 from. And so you guys at home, I made it up, and made it up more or less with the idea being that we would have a starting separation distance and we would pull the capacitor to another separation distance. Does that make sense, you guys at home? All right. So we are going to erase all of this. We're going to do it one more time, but this time we're going to try and focus on not leaving the charge in there, but leaving the potential in there, because the potential is going to be constant for a situation that's not isolated, but the potential difference is maintained. So let's put the isolated one off to the side here. So the force for an isolated, help me out here if I get this wrong, Q squared over K epsilon naught A, right? So that's force for an isolated one. So now let's do the force for a non-isolated one. Stays connected to the potential. First thing we're gonna do is still have Q times V over D. You have to work that in. Now this time we're gonna try and get rid of Q. So I'm gonna take and solve this for Q and replace it and get CV squared over D. Good so far? So now I want to get rid of C. So I put it in terms of the construction of the capacitor. And so I'll have kappa epsilon naught A over D times V squared over D. And we get a much different answer here. So combine this out and I get kappa epsilon naught A V squared over D squared. Now, V is a constant if it's connected to the capacitor. I'm sorry, if it's connected to the voltage source. But we'll notice that the force required to pull the capacitor apart diminishes quite rapidly because it's over D squared as I pull it apart. I don't know why that's true, but I can't fight the fact that that's what it is. What's interesting to me is that as I begin to pull it apart, it occurs to me that there's going to be a flow of charges. And I think the reason why the force goes down is as I pull the capacitor apart, the capacitance gets smaller. So there's less charge on the capacitor plates, which would affect the electric field, making it easier for me to pull it apart. So it seems to me it's easier to pull apart a capacitor connected to a voltage source than it is to pull apart an isolated capacitor. Now, just so you guys know, I've really not had this kind of conversation before. This problem has not come up very often. But as I looked through the literature this summer, it seemed like this is one of those things that's becoming more prevalent, this manipulation of the physicalness of a capacitor. They've done a lot to be talking about putting in dielectrics and changing the dielectric. I thought it seemed prudent for us to talk about this kind of problem too, since I think it'd be a new way for them to talk about it in the literature. Does that make sense? Like, this one hasn't come up in a long while, so maybe it's time. So this is F connected to V. Interesting ideas, though. I think this answers whatever was in the textbook. So what do you think, Alex? Well, you brought it up, so I was asking you what you thought. Good stuff? I want to point this out. These things right here, every parallel plate capacitor, it's easy for them to use this kind of stuff and ask you about the electric field. It's really easy. And since it's all linear, it's all fairly straightforward. I think that's a good thing for you guys to check out and to kind of think about when we deal with these kinds of problems. All right. Anything else on the homework that we haven't really talked, beat to death yet? All right. That's good for me. So here's what I would normally say we would do. Normally at this point, I would say that we would move on and start talking, and get prepared for a test. What I would really like to do is hold off on that and talk about current flow this week. Get a lab in on maybe Wednesday, do some current flow discussion today and tomorrow. This will likely be a reminder for a lot of you because we're going to talk about Ohm's law and resistivity. So many of you have had this, not all, but many of you have had this. And then have our test on Friday as promised, which will focus mostly on capacitance, but we'll have some multiple choice questions that are definitely going to deal with current flow. But I'm still going to focus the FRQ section on capacitance. Does that make sense? Then we come back, we'll be able to do more advanced Kirchhoff's laws and RC circuits. We'll have two and a half weeks to do that. There will be some interruptions in the schedule, I'm sure, when we come back from Thanksgiving, but I think that'll give us plenty of time for us to finish with a final test on all of circuits the Friday or Thursday before we go off to the break. I'm actually thinking about for us doing it on the Thursday before we go off to break, because I've already had a few folks say that they might not be here on that Friday. So I don't know if it's affecting you guys, but I'm expecting to hear from that soon. If you're planning on not being here on one of these holiday days, please don't keep it to yourself. I'm not going to be angry. I just want to know what I have to prepare for. Like, it didn't occur to me that FSA was tomorrow. So I've got like half my juniors out for the next 2 days. Just wasn't prepared. Okay, so then I want to switch gears. Yes, sir.
Would they ever ask us something like this for like a linear capacity, like the rings or?
No, but they will ask this kind of question for a non-uniform, like they can't ask it for a cylindrical capacitor because of the way it's structured, and they're not going to move they're not going to move the center around inside a capacitor. It just makes the math all wonky. So they're not going to do that. They have asked about spherical capacitors. And I did not even touch on spherical capacitors. And if you want, we can take a moment or two and talk about, I think I gave one homework question about a spherical capacitor. So, and it's not that I didn't want to, it's that I was getting a little bit of fatigue of doing the problems of how to talk about capacitance. And I knew once we got into actually how capacitors work, it's a little more hands-on and more productive conversation, but we should probably talk about a spherical capacitor. That would probably be what a good teacher would do. So you're stuck with me, but I'll try and do a spherical capacitor. So let's do that at least once. The only reason spherical capacitors are even interesting is because of a little mathematical anomaly that you get when you have a spherical capacitor. So we need to see what that anomaly is. You can't make a spherical capacitor in any real form because it's two concentric spheres. So how do you effectively charge it and discharge it? You follow me? You could kind of embed a wire here, and have it go through the one side and try and isolate that wire from the other side by poking a hole in the shell. But why would you go through all that trouble if there's no added benefit? And there's no added benefit to making capacitors this way. The reason we study them is because of a quirk you'll see with the mathematics. So let's get to that quirk because that's what's important here. Let's first say that we have charged the inside to a value of Q. So we have a electric field that's like this. I should show more movies. Have you guys liked the movies we've seen so far this year? Exactly. I never show movies. I never will show a movie. And it's not because I don't like watching movies. I can't believe if I woke up and came to school and all my teacher did was make me watch a movie, I'd feel like, why did I come to school today? Like, watch a movie. I used to think movies were great. I could get all my grading done. I just don't do it anymore. All right, so if you'll recall, there's several steps to calculating capacitance because we have to establish Q and V for our charged system. Yeah. Oh, yeah, I'm sorry. You're welcome. Someday, I'll have a new projector. Actually, I have a new projector. Someday, my projector will be installed. You guys do understand that I don't believe there's a chance at all of it ever being installed. I actually almost gave it away the other day. Okay, maybe you'll have better luck. Maybe they'll listen to you. Maybe they'll. I've already spent the money to get it installed, though, the $500. All right, so we have to do two things. We need to get an expression for the charge in terms of the electric field, and then we have to do the integration of the electric potential due to that field. So we use Gauss's law, and we use Gauss's law to get an expression for the electric field. So to do that, I have to establish the inner radius, and I'm going to call that A, outer radius as B.
Partners and Russian teachers and students, this is a test on the intercom system. Thank you for your cooperation.
So I'm just reminding us of the steps. So our first step is to use Gauss's law to get an expression for the electric field in terms of the charge. I don't really have to do anything when it comes to Gauss's law for this example. And I hope you guys remember that there's really not a whole lot to do here. That this is my expression for the electric field between the two spheres. It's just that of a point charge. Is that really it? I don't know when the bell rings. You know me. That is right? Oh.
Let's just say no and then just.
Okay, well, I'll tell you what, I'm just gonna finish this because it's only like 2 minutes and I'll just keep talking. You guys go to your next class and then I'll just upload it. And I will do this again tomorrow in class, but I just want to finish my thoughts. So you guys at home, you're welcome to hang or take off. You gotta go to another class, but I've got to do it. So then we have to take and just drop this in so I can integrate. And I'm going to get the integral from A to B of Q over 4 pi epsilon naught r squared dr, which when I factor all this stuff out is the integral from A to B of 1 over r squared dr.
We appreciate your appreciation.
Thanks. So all that's left to do here is write this as Q over 4 pi epsilon naught times 1 over B minus 1 over A. It's actually there because you get a negative sign out of it. I skipped a step. Sorry. You guys are all looking like crazy. Let me do this. This will be negative 1 over R evaluated from A to B. So what I'm going to do instead, you've probably never seen this, but I'm going to get rid of the negative sign and just flip the limits. It's something you can do. It just changes the order of your subtraction, which is going to give me Q over 4 pi epsilon naught times 1 over A minus 1 over B. That's my electric potential. Now, these are just little things that you're going to have to do to make this work. And the first thing is get a common denominator and add those things together. Okay, we have to. You'll see why, but you have to. Next, if you'll recall, to get capacitance, we have to take the expression for the charge I'm sorry, the charge, and divide by the expression we just got for the electric potential. Now you see why we combined the denominator, because we have all this. It's just going to give us 4 pi epsilon naught times AB divided by B minus A. That's the capacitance. It's kind of weird, but that's what you get as your response. Now, tomorrow, what we have to talk about is what happens as B goes to infinity. And we'll talk about that tomorrow. All right. So any questions about, I mean, there might be questions, but I just wanted to get it finished. So we'll pick this back up right here when we come back to class tomorrow. Okay. Bye, guys.